Okay, just kind of current events to expand on the extra credit pop quiz. Lake Oroville, as most of you should now be aware, is the largest concrete arch bridge dam in the United States, built in the 1960s. And like most dams, it has a spillway, which sits right here, that prevents the dam from being overtopped. Overtopping can result in failure of the dam itself. There's also a second emergency spillway here if you need more water out or if there's a problem with the original spillway. So that's the way things are supposed to work. Now, you actually have this in your notes at the very end. So, but I'm going to read this because it's an interesting history of how we got to where we are today. 3 environmental groups filed a motion in federal court 12 years ago, urging officials to require the emergency spillway to be armored with concrete, because at that time and to the present it was just kind of an earthen embankment. And what the environmental groups had said was that in the event of an extreme rain and flooding, water would overwhelm the main concrete spillway, which is the intent, and would flow down the emergency spillway, which it was designed for, but it would cause heavy erosion. And that would create flooding downstream and could result in a failure called loss of crest control. And loss of crest control means there's damage to the facility and the potential for major downstream flooding. Okay. Now, the response by the Federal Energy Regulation Commission rejected their request, basically because the groups, the federal agencies, state agencies that would have to pay for the repairs said that they were unnecessary. And the federal officials at the time said the emergency spillway was designed to handle 350,000 cubic feet per second. So the concerns were trivial. Keep in mind that number, 350. A lawyer for the Department of Water Resources said there's only 1 to 3 feet of erodible topsoil in the downstream area, and that erosion would not compromise the stability. The red is my highlight. With flows of 600 to 12,000 cubic feet per second, okay, which was about less than 5% of that 350,000, you began to have so much erosion occurring that they had to evacuate 185,000 people. Okay, so what went wrong? Well, if we look, first of all, let's look here at the primary spillway. As that primary spillway had opened up, this is the first thing to go wrong. There's a lot of water that's coming down, not somehow causing a lot of erosion. When they shut that down, they found, of course, there was a major failure of the primary spillway. Okay? And so when you look at that, this is a man for scale, they had to shut it down, and of course that meant they diverted water to the emergency spillway. But as the emergency spillway was doing what it's supposed to do, there was beginning to be signs of failure of the concrete spillway as erosion was starting to occur in the spillway itself. And you see 2 large areas of erosion right along here and here. Okay, so you see this big hole that's developing. Now notice right now when this picture was taken, there's a road right here, and the road was being undercut. That is the road a little later. We're going to come back to this road because it's a good kind of marker, which is just downstream from the dam itself and part of the emergency spillway. So here's that road, and now we see there's erosion that's has gone up right to that concrete base and also has split the road itself. All of this area has been eroded. Here you see major erosion approaching the spillway itself. And the problem here is not that the dam will fail. The dam actually was never in danger, but rather because of this headward erosion, that is to say erosion that's heading upstream, the worry was that the concrete wall of the spillway, which is this wall right here, would be undercut and fail. Okay. Now, in that case, what you would have is a catastrophic lowering of the lake by tens of feet instantaneously. And so that would be a catastrophic failure of a portion of the dam, but not the dam, the main dam. Okay. And so this is, we can actually see big chunks of concrete have already begun to be undercut in that wall, that concrete wall that is the spillway. Notice there's a lip here. That lip was supposed to avoid undercutting, but clearly it didn't. And so as we see this erosion, which was supposed to be trivial, one of the things that hopefully you can see is this is the contact between the bedrock down here and the alluvium. So the first thing is the fact that there's only 2 to 4 feet or 1 to 4 feet of alluvium was clearly not the case, suggesting that the lawyer at least did not have a good idea of what the nature of the material was. Maybe more, well, okay, we'll just see this. So what did they do? Well, they had to basically truck in concrete to kind of fill holes here, and the helicopter was dropping rocks quite literally to prevent the undercutting. Now, this is some of the concrete that's being spilled into the hole. And what I want you to note, again, first of all, is that contact between the alluvium and the bedding. And secondly, look at that non-erodible bedrock. Well, clearly the bedrock was highly erodible. And one of the things that's striking is the amount of fracturing in this bedrock. And in fact, the fracturing is more or less parallel to the flow direction of the spillway. So once the bedrock was exposed, you had conduits that made it very easy to erode this bedrock. So the whole statement about the lack of erodibility was just geologically wrong. Okay, this is just some of the helicopters that are taking the rocks. So what we're looking at now is to try to fix something that was recognized at least 12 years ago, but most likely because it was just considered too expensive, fixes were not made, and it was in the absence of good geological information. Okay, so it's a case study worth noting, and obviously a current event. Okay, well, another current event, back to California again, is coastal erosion and landslides associated with the coastal erosion today. Now, when you build along the coast, there's always this question about how close do you go to get an ocean point view. These people got lucky. They got an ocean view when the house in front of them decided to go elsewhere. If we look at landslides, well, they're all over the place. Although, as we'll show you, certain places. Landslides here, deadly landslides in Brazil. And the argument here is that the president said we need to remove people that are living in areas of risk. Okay, so that's the first thing, land use planning. Okay, fatal landslide draws attention to mining, the failure associated with the mine tailings. This is a huge problem. Here again in the Himalayas, 10% of the Nepal hydroelectric capacity was destroyed. This was the largest earthquake and earthquake-generated landslide in Nepal. We had the most deadly landslide in U.S. history in 2014. The people that were ahead of the emergency management said this came out of nowhere, no warning. We'll think about that. 190 missing during monsoonal mudslides. Colombia, 50 killed. Guatemala, maybe 500. And here, possible criminal misconduct. Okay. Myanmar, waste collapse, over perhaps 200 killed. In Japan, hundreds killed when a failure of a large waste mountain. So one of the things that's quite clear is that human activity is a major issue with respect to landslides. We're going to talk about how you can make a landslide worse, but certainly one of the things is we need to consider where people build, and especially how we build man-made piles of debris, because many of the fatal landslides are the result of failure of man-made debris. In fact, the idea of natural disaster, according to the Secretary General of the UN, is becoming an anachronistic misnomer. There really should be called unnatural disasters because of the role of people creating more severe natural disasters. If you look at the number of fatal but non-seismic landslides, we're going to kind of ignore earthquake-generated landslides for a second. Almost 33,000 people were killed in a 7-year period. Orders of magnitude more than had previously been recognized during this study. And where did they occur? Well, basically they occur in tectonically active areas. And what that is are areas of high relief and combined with intense rainfall. And lastly, of course, high population density. Okay. Now, if you look at when landslides, or better said, fatal landslides occur, there's actually seasonality for these non-seismic landslides. And they increase in late summer. And that increase is associated with the monsoons. The monsoonal rainfalls, especially in Asia and in North America. And in fact, if you look at that, the cyclicity, you realize that this is a long-term pattern. Okay, a lot of rain and failure. Now, if you look at just the last year, the black line is the number of landslides. That's over here. Okay, and we ended up with something like 450 fatal landslides last year. We ended up having 2,200 people killed globally. Okay, so the numbers are high, relatively low compared to earthquakes, but a major problem locally. So where do we have them here? Well, along California, along the Himalaya, along the Appalachians, and then in a few other areas like in Colorado and the like. Okay, so we're okay here, unless you've noticed on Scott Street next to the bio, there was a significant landslide that they're still trying to fix. Okay, so what do I mean by landslide? Okay, well, rapid downslope movement of rock and soil that's more or less coherent. Okay, now it turns out landslides are one of a variety of processes that are the result of mass wasting. And mass wasting is the removal of material by gravity. Now you might ask, how does that differ from erosion? Well, erosion is the removal of material by a fluid or ice. Ice, air, water, a mobile agent. Whereas gravity just things fall, and depending on the nature of their density, they then can move laterally. So there are landslides, but there's other things as well. So we'll talk about the spectrum of processes here. It is a common misnomer that all of these processes kind of fall into the term landslide. That's a sloppy way of using it. But it's not an uncommon way of using it. Now, in the U.S., this broader sense of mass wasting causes a couple of $1 billion a year and can result in 20 to 50 people killed yearly. Globally, maybe 2,500. Okay, so this is the classification that I'm going to use for types of movements. And notice slides are but one type. we've got falls and topples and lateral flows and then complex. So we're going to start with bedrock involved, okay? So we got rock fall, rock topple, rock slide is basically like a landslide, rock creep, okay? For unconsolidated material, and there's again a little bit of a confusion between how, say, an engineer would use the term soil and a geologist would use the term soil. An engineer refers to soil as anything you can dig up with a backhoe, which from a mechanical point of view may be quite reasonable. We tend to think of soils as being something pedogenically altered, so that we think of the A horizon, the B horizon, etc. What engineers call soils, or we would call unconsolidated deposits. Okay, and so these unconsolidated soils, if you like, can be coarse or fine. And now we're looking at things like debris slides, earth slides, debris spreads, debris flows, or earth flows. Okay, so as we're going to see, the fatalities are often not just of a rock landslide, but often as these materials will change with time. Because what we're really looking at as we go from top to bottom, we're looking at decreasing viscosity, increasing fluidity, if you like. And so the more fluid the flow is, or rather the mass wasting, the more rapidly it will move and the greater the lateral extent. This is somewhat like a pyroclastic flow, for example. So we're going to see that these things can actually change from one to another, and so some of the worst disasters are actually maybe not landslides, but things like debris flows. Okay, so here again we're looking at this, but we're looking at it kind of from a little different view, slow to fast. Okay, and so when we look at that, we see rock slides, earth flows to debris avalanches. Okay, now we're looking at things that are coming in as a rock or debris avalanche. These things are moving at exceptionally fast speeds, and so they are going to be the most disastrous, most deadly. Okay. On the other hand, we've got creep, which is quite literally just kind of creeping along, and then we have this transition in between. Particularly in terms of flows, think about creep to, let's just say, a debris flow, which could be either a earth or mud flow, to debris avalanche. Okay, this sequence here. And we also sometimes get a rock slide to a rock avalanche. Sometimes the rock slide will transform into a debris avalanche as it moves down laterally. So these are the most dangerous and most deadly. Well, a rock fall can be a real problem if you're underneath it, but they don't fall very far. And so clearly from an engineering point of view, you want to minimize this. A rock topple kind of just pivots. There's no big difference. We usually know where to look, and as we'll see later, we'll talk about things you can do to prevent these things from happening. For slides, the one that I'm going to focus on most is a rotational slide, or ones rather, rotational and translational. These are the most common kinds of landslides. There's also a block slide. Basically here we're looking at a failure within relatively consolidated material, although it can be soil. And more specifically, it's failing along a particular zone of rupture, along a thin layer of intense shear strain. So it's not moving as a fluid, but rather as a relatively coherent body along a failure plane. Okay, and the big difference between these two is simply the shape of that failure plane. Okay, a translational slide is one where the failure plane is relatively planar. It isn't horizontal, but it's planar. It's not curved. And as you might expect, it usually is going to occur at a zone of weakness. So one of the weak areas for failure to occur would be the contact between bedrock and the overlying material, unconsolidated material, sometimes called colluvium. Okay? So that's going to be one area where you could predict the possibility of a plane of failure. Another one, though, might be, as we talked about in the third lecture, I think, simply a pre-existing plane of weakness. Maybe bedding, maybe joints, maybe foliation, etc. So we're looking for something that has a planar fabric to it. Okay. We actually talked about that where we said, okay, look at this area here where we've got foliation planes, where those foliation planes have been undercut and a translational landslide could occur. Okay. Now, a rotational landslide is one where the plane of failure is kind of spoon-shaped. It's curved with the crown on the crest, and then as that material fails, it then kind of overrides, so we can look at different parts of this landslide, and the crown or the main scarp, we're going to see examples of that in a moment. There can be secondary scarps. You've got the head, which is the top of the landslide, and we have the toe, or the foot, which is the downslope side. Okay, and so we're going to look at examples of these and see these different parts. I'm going to go into some detail in discussing this because there's actually going to be a homework assignment on your mapping landslides. Now, I have to add that the homework assignment that some of you have seen already on Simonton is actually from last semester, so don't worry about that. I'm going to change it slightly, and it's not going to be due for another month or more. Rather, I will be sending you emails, and we'll talk about the homework assignments in class as they are developed. So the first homework assignment will be right after the exam, and it'll be on landslides. And then we're not going to get to homework assignment on flooding until later. Okay. Now, one of the things that is characteristic of a rotational landslide is that curved surface. And because that surface is curved, that results in a rotation as what was the horizontal surface is failing down. We see this in structural geology where we talk about a listric fault. A listric fault is one that on a very large scale is rotational. We talk about a large half-graben perhaps in the Valley and Range, or rather the Basin and Range province. Here it's a much smaller scale, but it's the same process. A curved plane of failure gives you rotation. Okay. And so here actually is the previously horizontal surface, and here's the plane of failure. Okay. So this back tilting, if you like, that you see with the trees is the result of that rotation, and that's evidence at the surface of that curvature at depth. Okay. Now, we talk about a slump. Again, the terminologies are a little vague. I'm going to the distinction here, and it's one I'm not going to get into too much, is that what they call a slump is that portion of the failure that has actually been cut by the rotational failure. And then where it overrode that onto a pre-existing surface, where we talk about the toe, they're calling that a flow. And it's certainly true that the material here tended to fail more brittly, tended to break up into distinct blocks, but by the time it's hit the lower part, it's flowing out. So certainly rheologically, these different parts of the landslide are behaving differently mechanically. Okay. The slump as defined is where you've got multiple planes of failure. Okay. So you're going to see little steps, and you might see that right here. See, you got one failure here, 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 here. Each of these is a little step from the original surface. So strictly speaking, that's what a slump would look like. Okay. In a more general sense, that's the way most of these rotational landslides occur. Okay. Having said this, we're seeing a gradation from a landslide to some type of flow, earth flow, debris flow, as that the mechanical properties of the mass movement has changed. And how has it changed? Well, most likely you're looking at the incorporation of water. And so as you add water to this debris, it becomes less, actually more ductile, if you like. It becomes more fluid-like, and it can move out and expand at the toe. So here we have a large crown. This is the main slump. Here's another failure and another failure. So there's multiple ruptures. You can see in the green where those little steps are. And then down here, you've got that flow portion. Didn't flow very far, so it wasn't very fluid, unless, of course, you had a house here. But this would be an example of a slump with various parts of it. Okay. Now, this is a little more typical. It's, again, a complex landslide consisting of different types of material and different types of movement. Here is the major zone of failure. And this is somewhat analogous to what I'll be having you do on your homework assignment. There's another arcuate slump here, arcuate zone of failure, rather. So we've got a couple of smaller crescentic zones of failure. If you look right in here, this, by the way, is a LiDAR image. And LiDAR is a light-reflecting radar that gives you a very precise three-dimensional view of the ground surface. And because it's digital, you can shade it in different ways to accentuate different pieces of the topography. So think of it as a picture of the Earth's surface, but largely devoid of vegetation. And where things are smooth, on LiDAR, they are smooth in terms of the actual ground. And so we have this zone in here, right along here, that's really quite smooth. That is actually a zone where sediment has ponded. And so the older the slide is, the more likely some of these areas where there's been back slumping have been filled with sediment. So that's one of the ways we can look at relative age of landslides. And that's an important thing if we're trying to work out both the chronology of the landslides and whether the degree to which they represent a modern hazard. Okay. Now along here we've got a shear. So this is really kind of like almost like a strike slip fault. It's called a minor scarp along here. And then notice here, as it comes out here, it is a flow. And you have these little wrinkles that are pressure ridges, and you also have a series of radial fractures. Okay? So there's transverse ridges and cracks and radial cracks. Okay? And so the transition, in fact, you can even see a bit of a block here from more blocky to more flow-like is occurring right along in this area here. Okay. So this would be an example of that type of flow. We see another one over here. This one has a crescentic area here, and then it looks like we've got something over here. So what we're looking at here is cross-cutting relationships, where a newer slide has cut into an older one. Also, notice the degree of dissection of that scarp. The older that scarp is, particularly the head scarp, the more it's going to be dissected. So again, a criteria for relative age. So here's some of our mass movement that we're interested in. A very fast would be a debris avalanche. A debris flow or earth flow is a little slower, and then creep and lateral spreading can occur at relatively low rates. Okay. Now, the distinction between a debris flow and an earth flow really has to do with the nature of the material. A debris flow is more poorly sorted, has larger range of fragments. An earth flow tends to be smaller fragments and less, little better sorted. It's still poorly sorted, but less of a range of size. Okay. So let's look at a debris avalanche. That's really our worst case scenario because it's moving very fast. It will bury people. It will bury whole villages. Okay. And so here is a debris avalanche that occurred in 2014 in Washington State. And we see the large scarp. This again is a LiDAR image. And what we see here, this is the extent of that avalanche. And notice we're looking at big blocks, pieces of the failed material being brought out hundreds of meters, well, actually almost a mile away from the failure. If you think back, we actually saw something like this on an even larger scale. Where? Where have we seen something like this in a previous lecture? Where? I'm sorry, where? Yeah, with volcanoes. Which volcano? Not Goma. Mount St. Helens. Yeah, remember that big avalanche? And we looked at, there were just these big blocks of material that were pieces of the mountain. Okay, and so what you don't see is a large number of houses and 44 people killed as it jumped over the river and sped across. Okay, now another type of relatively rapidly moving mass movement is an earth flow or debris flow. They have similar characteristics, so I'm going to kind of lump them. And what we have is, again, a head, and then they tend to funnel down a narrow chute, and then there is a, sometimes referred to as the toe. So we go from a zone of depletion, which is basically the sediment is being removed, to a zone of accumulation. Okay. So it's the head to the toe. Okay. And this is the area that's been, scoured, and this is the area where there's deposition. Okay. Now, here's a case of a destroyed house. Here's that source area, and notice how thin that track is. We call it a debris flow track. You can see it coming down here until it widens out. Okay. If what you need to get a debris flow is you need a steep slope, moisture, and a lot of unconsolidated regolith. And regolith is just one more word for colluvium due to weathering and accumulation. Okay. Now, the reason why we tend to get them narrow is they're often the places where this regolith or colluvium accumulates is along little gullies where it's moved in by mass wasting. Okay, so little tributaries, not even ones that would have water typically, are being filled by mass wasting. And so what that does is it provides us with this linear source of sediment. And what's it waiting for? Well, it's waiting for a lot of rain or an earthquake. Okay. Now here is an image of one. Here's the debris flow. Here's the head, the chute, and the bottom. Let's look at it a little more closely. Actually, this is just, again, kind of trying to show head and toe. Let's look at each of these elements. Okay. The first element is the head or the source. So we see this is actually at the head of a little tributary. Okay. And so it's all been excavated. And as we look at the chute, this is where it's mainly in transit, but one of the other things I want to point out is the presence of a levee. Okay. Debris flows typically have levees, and where have we seen levees before? Well, we've seen them in andesitic flows. We saw them in volcanic mud flows, lahars. The only difference between a lahar and a debris flow is that one is associated with volcanism and one isn't. Now, the other difference is lahars tend to be bigger because they tend to have a lot larger source of material coming through. But mechanically, they're moving the same. And so this levied channel is flowing into this depositional lobe that's expanding and got the little crescentic pressure lobes, etc. Okay, so these are all features we've seen before, but in a different context. Okay, so here's that gully, and here's where the failure occurred and houses being buried. Okay, here's where they tend to occur, right along the uppermost portions of a drainage system, where you might not even have a creek per se, but rather just a little hollow. And those hollows are basically going to then be excavated during periods of high rain. Okay. Here we see vegetated and non-vegetated areas. Non-vegetated, these were the head, chute, and depositional pods of these debris flows after a hurricane has come on shore and rained in the Appalachians. Okay. In fact, these little red places, each are debris flows. And you can see they are really just reactivating the uppermost part of this drainage system. Okay. Lateral spreads tend to be a little slower, although they can range a little bit in speed. But one of the differences is it looks like a translational landslide. To a large extent it is, but it's a special kind of translational landslide. It's one that's almost horizontal. And so it's spreading. So how can it spread on such a low slope? It's spreading because of liquefaction. Remember, liquefaction is the loss of shear strength due to cyclic loading. And so that's going to occur typically, if it's on land, typically it'll be during an earthquake. So liquefaction is a common way to cause the lateral spreading of the uppermost slab. Usually it requires a free face. See how this has broken up into kind of blocks as this is slid down. You need a free face. That free face is typically a river, such as we have up there, or maybe a bay or an inlet. Okay, and we've got some good examples of lateral spreads when we look at, or had some good examples when we looked at Anchorage in 1964-65, where you had liquefaction of the bootlicker clay. So here we had the liquefied soil, and we've got these blocks breaking towards a free face. This is, in fact, that lateral spread due to liquefaction right here. And here are those blocks. And this is a large lateral spread, and if you look at it closely, you see these arcuate blocks. And where was it flowing? Well, it was flowing into the bay. Took a cross section. There's the Turtigan Heights landslide, which is a type of lateral spread due to liquefaction due to the Good Friday earthquake. Okay. The slowest of our processes is creep and or solifluction. But creep is associated with the expansion and contraction of clays, particularly smectite clays or montmorillonite clays. These are the clays that have a lot of space between the individual clay sheets. And so that space can fill up with water and expand, and then as it dries, it'll contract. So the expansion on an inclined surface is going to be at right angles to that surface. So we're going to move up like this. When it contracts due to gravity, and it's going to go straight down. And so over time, there's a very slow creeping downhill. Okay. That slow creep can actually be observed by looking at trees that are curved. And as they started growing like this, but as they gradually move down slope, they keep bending up. You can see man-made features that are tilted. You can even see the bending of rocks as that creep is going along the surface in that weathered zone. Okay. We can also see what are called soil ripples. Quite literally, these are wrinkles in the soil as it's moving down. Now, it gets a little confusing because once you've got these ripples, cattle and sheep tend to walk along them, and it accentuates the individual soil ripples. But these features are independent of animals, and they are quite literally the rippling of the soil. Okay? So these are some of the characteristics of these different types of mass movements. So what I want to talk about now is the triggering mechanism. What forces them to fail? Well, the first thing is oversteepened slopes. Okay, we've increased the steepness, and that is usually because of erosion. So the failure that was occurring along the Palisades, along the Gulf, or along the Pacific coast, was due to erosion by ocean waves. In other cases, it could be by glaciers or very commonly by rivers. So oversteepen the slope by eroding. The next thing is you might try to weaken the slope by increasing the pore pressures. And you do that by saturating the interstitial spaces by either snowmelt or heavy rains. Okay, so now we both have increased slope, which of course increases the shear stress due to gravity, and we've caused it to be saturated, which decreases the shear strength due to increased pore pressures. And now, maybe let's make it even worse. Let's have an earthquake. Cyclic loading can generate liquefaction, or it can simply weaken the sediment, in either case causing failure. Okay. Now, in some cases, it's not an earthquake, but a volcanic eruption. Again, we saw examples of that. The bulge in Mount St. Helens with the catastrophic earthquake that occurred there. There's several examples of major earthquakes killing, in the case of some landslides, a major earthquake causing landslides, killing tens of thousands of people. Now the other thing is, why don't we put some weight on that slope to try to make it even heavier? So we could do that, well, one, just by rain and increasing one, but we could pile up material. We could maybe have man-made structures. There's a variety of things that we could do that inadvertently, but due to ignorance, can trigger an earthquake. Okay. So, like the case studies that we looked at in earthquakes and in volcanoes, I want to look at some in landslides, and I do it for the same reason, to try to answer the question, what are the geologic conditions that led to that event? What were the triggering mechanisms that led to that event? And what were the lessons learned from that event? Okay. So we're going to start with Vaillant. Vaillant in 1963 was a landslide that resulted in massive flooding downstream of a dam. Now the irony is the dam was fine. It was a very well-built dam. The slide did not occur at the site of the dam. It occurred at the site of the reservoir. And so you had 2,500 people killed because of the water that overtopped the dam, because of the landslide filling the reservoir. Okay. So what caused that? Well, I'll show some diagrams, but weakness within rock units, raised water level, and therefore pore pressures, decreasing shear strength. Okay. We'll skip that. Here's a picture of the dam in the reservoir before failure, and this is the dam reservoir after failure. Literally, here is this lobe of sediment that came from here and deposited here that basically filled this part of the reservoir. Okay. A map view, orange is the reservoir itself. This is the area that failed. Okay. And it basically, oops, overspill or filled this portion of the lake, which then caused downstream flooding. Now, a couple of things. There was an old landslide there. So the first thing is the landslide occurred along where there was an old landslide. So that's a pretty good sense. In fact, this is the ancient landslide. It was largely reactivated. Now, the second thing is the strata that were here, the bedrock, if you like, was in part, well, there was a fault here, and formed kind of a syncline, a faulted syncline. So the bedding was towards the dam. I'm sorry, towards the reservoir. But look at the shape of this reservoir cross section. It's kind of a U shape, then a V and a U shape. Well, this was a glaciated area. So this was the glacial U-shaped valley. After glaciation, we then began to have down cutting. So this is a not atypical cross-section of glaciated valleys, particularly in tectonically active areas. Okay. Now what that does, it exposes not only the inclined strata, but also exfoliation joints that had occurred. Exfoliation joints form where you've removed pressure, and so there's an outward motion that causes an extension. And they can often be curved, and in this case, they were curved because of the shape of the U-shaped valley. So now we've got two planes of weaknesses. the bedding and the exfoliation, both of which are dipping into a free face. Okay? It's not a good condition. Okay? Here is the dam downstream. It is, or was, and I think maybe still is, the highest thin arch dam. Okay? It looks fine, even now. Okay? That was a well-built dam. It was poorly placed, because here is the landslide debris inlet. Here's the scar. Here's the backside of the dam. Okay? This is the plane of failure along which that slip occurred. Okay? That's this right here. Okay? And so now we're looking into it, and here's that head. Actually, it goes all the way over to here. Okay? And there's the landslide debris. And what we're looking at here, we're looking at before and after. Okay. And of course, all the water that was here over top the dam. Now, one of the things that caused this to happen was the geometry of the potential planes of failure. But the other thing is the increased pore pressures. Why were there increased pore pressures? Beg your pardon? I hate to say it, but you're going to speak louder.
Melting glaciers?
Melting glaciers? No. That melting glaciers actually caused the incision, that kind of a V shape, as the glaciers receded and the water coming off the melting glaciers incised that U-shaped valley. Something else.
Maybe the fault.
The which?
The faults.
The fault?
Yes.
Yep.
From the dam.
From the reservoir. What happens when you dam a river? The water rises. What happens to the water table in the adjacent areas? It rises. So you took an area that was adjacent to the valley, that was relatively dry, and you caused it to become saturated. So you've elevated the pore pressures. So the combination of the elevated pore pressures, which is inherent in any building of a dam, that's kind of one of those side effects, plus the unstable geological setting caused the failure to occur. And actually, they were monitoring the movement of that slide and looking at how it was correlated with increased pore pressures. They just didn't predict it failing as quickly as it did. Now, one of the triggering mechanisms can be an earthquake. And it can cause a debris avalanche that can extend large distances and arguably looks and probably is comparable to a lahar. Remember Armeno and 22,000 people killed due to a volcanic eruption. Well, here's 18,000 people killed in this village here, these villages, in Peru, off the Andes. Now, one of the points that I would make here is, first of all, there was a glacier, and there was a lot of meltwater, and in fact, the purple was an avalanche that occurred in 1962. 8 years later, the brown came and completely buried the town of Yungay. So the first thing is, these are not uncommon events. Now, what made this one particularly bad is that as the shaking caused failure of the glacier and the material, it's coming down very fast, and then it hits a bump. Well, you might think speed bump, but what it really was, it was a bump that launched that into the air. And so now you've got this moving body of debris that's launched into the air and then falls down. What does it fall onto? Air. And so it rides on a compressed air. So it's literally fluidized. So we're looking at this thing that's bouncing along this air-trapped corridor, moving very fast and, of course, causing tremendous loss of life. This block slide here, I think I'm going to skip it, except to say that the largest number of people killed in North America was in Puerto Rico, and it was a block landslide with 120 people killed. Now, the reason, actually, I probably it is worth pausing a little bit here. When you see an event like this, you've got to ask yourself what caused it. And the reality is there's rarely one single cause. In this particular case, contributing triggers include heavy rainfall. You had a tropical storm coming in, so you've oversaturated or increased the pore pressures. The geologic structure, well, you had inclined beds that were weak, particularly little clay inner beds. They're the worst thing you can have, okay? And over-dip slope. And what that means is the slope is greater than the dip. So you got a free phase, okay? You've got zones of weakness. Oh, and then let's add leakage from water pipes and a lot of cesspools and septic tanks. And so the development that was on this area was also contributing to the increased pore saturation. So probably the trigger was the heavy rainfall. But the underlying factors were geologically unstable material combined with land use practices that were making that material less stable. Okay. Okay. La Conchita in California is one of my favorite case studies. It's sitting along the coast, and in fact, this is a low, kind of a little terrace. If we were to look a little farther down, we'd actually see the beach. So this is a hill and then a relatively flat area, a low-lying terrace along which a subdivision has been developed. And so here's a road that's coming along here. And first thing you might notice is some kind of white scars. Well, that's never a good sign. In fact, this scar suggests there probably was a debris flow that came down here. This is a pretty big scar. And oh, by the way, when you build a road like this, what do? Well, you cut into it, and so you over-steepen the slope. So you're already seeing something's a little worrisome. And then look at this area down here. This is actually a bit of a cone. The fact that the colluvium goes up like this. Why is that little high area there? Well, it's because that must have been a zone of accumulation from this. Okay. The last thing is, and it's harder to see here, but there's a great big scarp that I can't seem to draw. That's kind of arcuate shaped, and that's maybe the worst sign of all. So sure enough, in 1995, that scarp that was here has now reactivated, and now we have a large flow or slide and some flowage coming down and burying some houses right along in here. That's the 1995 event. Okay. 10 years later, a portion of that slide failed, and now it buried even more houses. Okay. So here's that 2005 slide, and it's vegetated a little bit, and this is a portion of that 95 slide. So one of the things is you see that the foot or toe of the slide are very different. So these are actually two different slides, even though they're occurring in the same place. We'll skip this. So let's look at that. first of all, look at this right here. Look at this arcuate scar. Then look at where that slide occurred in 95. Okay, so that's the reactivated portion of a larger prehistoric slide, or larger slide, better said. And this again gives you a little better feeling for the location of the subdivision. Okay, so what was it? Well, we had this tremendous amount of rain and more rain, and then it failed. So we're pretty sure that ultimately the trigger was too much rain, oversaturating of a slope. But again, a pre-existing landslide. Okay, so the area in blue is that landslide, and the area of damage is right here. Okay, here's that toe, right along here. And what you're looking at is some houses that were buried. And so what do? Well, of course, some of the houses are gone. These are just some of the houses that were buried there. Here it is. Okay. Well, you build a retaining wall. Except when the next slide came, it didn't hold. So the response to the first slide was clearly not adequate. Okay. So the second slide comes in and just goes right through it. The second slide, again, big rainfall event. Okay. And failure of a reactivated slide. Okay, and that's now, it doesn't really stop here, it extends farther on. This is a bad, yeah, here we are. Look how much farther it extended than the original one. Okay, in fact, this is looking down slope. You see how much of the subdivision was covered. And notice what we've seen before. Look at those little pressure ridges. That's more typical of a flow, particularly a debris flow. And what we're looking at is the transition from a slump to a debris flow as it came down slope. Okay, so here we have a nice slump with very little fluidized movement, very little flowing. Okay. It was a deep-seated slump. Okay, and it came down and it caused multiple failures, and you can see that kind of stair step. Okay, 12 houses were destroyed. In 2005, 13 houses were destroyed and 10 people were killed because it basically morphed into a debris flow with little levees and lobes, etc. Okay, so this is the before. Just before 95, focus on this. Okay, failed here. Okay, well, what's the deal? Well, first of all, let's remember that this whole area is up to here at least, is a landslide. And, pardon the overlap, there have been landslides going on at least since 1865. We say that's a prehistoric landslide. But in fact, although its origins probably go back way before, it's been moving ever since we've had records. The Southern Pacific kept getting the train. In fact, a whole train was buried when a failure occurred in 1909. It continually had caused slumps and failures. So this is not an area that should have been unexpected. This is what happens when you get these big, massive, complex landslides. They are reactivated. And although they're often, these big landslides are the result of a different climate, they're often Pleistocene features. Reactivation of these features by piecemeal, but here and there, occurs under present-day conditions, especially if you do something, either you as a through anthropomorphic effects or just the odd rainfall event weakens the slope. Okay. So They've looked into what could they have done, but, well, one possibility is just do nothing, which is, in fact, what they have done. Okay, it will eventually cause hundreds of millions of dollars worth of damage, and most likely would destroy about 30 of the homes. Second thing, move people out, make it a park. The third thing, regrade that portion of the slides that occurred in 95 and 05. It's going to cost about $50 million to do that. Okay. You could regrade the entire area for about $200 million. Well, now you're into this cost benefit. So how much is 30 homes worth, or how, actually you could do that now. How much is the lives lost? How much risk are you willing to take? That goes back to the dam in Oroville. It was too expensive. We'll take the risk. Besides, somebody told us it's not a problem. Okay. And so this is the thing that we're always running up against, trying to figure out how to take geologic information to get an accurate assessment of risk. Now, ultimately, the scientist isn't going to be able to say what is an acceptable level of risk. That is made by public officials and the public in general. Well, what the scientist does and the engineer does is to give you a valid accounting of the magnitude of the events and the probability of the events, so you can make an informed decision about what you're going to do. Okay. There's a couple of settings that just geologically cry out that you may not want to build there. Alluvial fans are one. Okay. These are clearly areas where a lot of debris, in fact, they are built up from the accumulation of debris. Okay. Now, having said that, in fact, here's a little debris flow that's coming down. Remember the parallel levees and the kind of digitate toes. Here's some trees that are buried. I mean, this is not an ancient process. This is ongoing. Okay. So what do you do about it? Well, unfortunately, it's often the flattest area in an otherwise mountainous terrain, so you build on it. That also happens in LA, by the way. There was a University of, Caltech geology professor. He came in from someplace in the East Coast, bought a house, invited the whole faculty over to show off the place. And he said, one of the reasons I bought it was this great big boulder that's sitting in the back. It's a great landscape element. And so Dick Johns, the chairman at the time, said, have you ever wondered how it got there? He's building on an alluvial fan. Okay. Well, in the northern part of Venezuela, along the coastline, we've got a tectonically active margin that has resulted in a large number of valleys that are providing debris flows, which is the place you build your cities. Okay, and so this is one of the cities, Carabaleda. Now the problem here is that in 1999 they had a lot of rain, and a lot of rain, and a lot of rain. And the net result of this torrential rain was you had debris flows and flash floods coming down onto these alluvial fans. 19,000 people were killed. Okay. If you look at this area, here are the older flows, and this was just the 1999 flow. And the size of the boulders, I mean, golly, they're huge. Okay. And if you look at the thickness, you can see in some cases up to 7 meters of debris was deposited during this event. Okay. So here we see the material, and we can see that in some cases, whole houses are buried by these flows. Okay. Now, some, of course, were destroyed, and it wasn't just the debris flows, it was water as well. But take a look here. This is the foundation that was built on top of exhumed debris flows. Think back of Armeno, where you've got Lahar building, Lahar building, Lahar. We can even go to near Seattle, where old volcanic mud flows are where we built our towns. So this is one of our clues. Also, take a look here. This is the mud line. So even where you're not getting the big boulders, you're getting a lot of mud-laden waters. Okay, so these are major problems with respect to where to build. Okay, you can see some of the damage. Okay, well, that gets into an interesting question. What do you do with all these cities in Venezuela that are along the coast that are built on areas that are designed to be flooded and accumulate boulders? That's a hard one. You can try to build dams to try to intercept the material. You can move. You could try to build diversions to try to deflect it. But these are hard choices because so much of the economy of that region is dependent on those places being there along the water. Now, this is an earthquake-generated landslide that became a debris avalanche that filled the valley. Now, it actually created lakes. These are sometimes called quake lakes because they dammed the area. So it's not too different from what we saw in Vaillant. The difference is that there was a village here. And so you had 1,000 people killed here, and large numbers were killed throughout the region because of these earthquake-generated failure. And also, the quake lakes themselves caused upstream flooding. And then, just to kind of make things worse, as the upstream area was flooding because of the landslide dam, eventually it overtopped the dam and it begins to cause downstream flooding, sometimes catastrophically, as that landslide material is dissected very quickly. So these are major problems. Okay, and you may recall, let's see, I had a newspaper clipping that I kind of liked, and it was ecological landmines. It's our fault. And it was talking about the Pakistani villagers who were saying that we overgrazed, we removed the vegetation, we added to the problem. And certainly that's partially true. But these areas with monsoonal rains, or in this case earthquakes, or both, plus very steep slopes, are just prone to fail. And so again, where do you put people? Okay. I'm going to stop at the Washington State slide. It's time for you to go home and study. But before we do that, does anybody have any questions? Yeah, hang on just one second while I save this.